everyone to the MQ seminar. I'm pleased to present Grace Yan. She's Associate Professor in Civil Engineering of Missouri University of Science and Technology. She's the Director of Center for Hazard Mitigation and Community Resilience. She's also the Director of Wind Hazard Mitigation, which I guess is WHAM, laboratory, that is home to a large-scale tornado simulator. From an engineering perspective, she simulates different natural hazards, like tornadoes, hurricanes, storm surges, and floods, numerically and experimentally investigates their actions on the built environment, and studies vulnerability in communities to natural hazards, as well as develop innovative approaches to mitigate and adapt to climate change impacts. She promotes convergence in scientific and engineering research and community engagement to enhance national community resilience and address worsening hazards caused by climate change. Welcome.
Thank you. I became a professor this year. I apologize for the old information. Ladies and gentlemen, thank you so much for coming. And first of all, I want to thank Director Malendor for giving me this opportunity to share my passion with you. Coastal resilience and tornado resilience. Today we'll focus on tornado resilience. Maybe another time I will come to share with you the coastal resilience. Why did we look at tornadoes? In tornado-prone areas, tornadoes can be everywhere at any time. It can occur at anywhere, right? So when you are watching a radio show, you wouldn't expect a tornado warning, but it can happen. Tornadoes, they can toss your cars to higher elevation. They can destroy your houses ruthlessly.
No, I don't change.
Yeah, this is the new Twister movie.
This is the new Hollywood movie Twisters. So although we have a high confidence to tell that future wildfires and future hurricanes will become more severe, the current climate modeling is still too coarse to tell the tornado intensity will increase or not in the future. However, even based on the previous tornado events, we can tell that we are seeing more tornado outbreaks. We are seeing more individual tornadoes in a single tornado outbreak, and we are seeing more surprising tornado events. One example is the 2021 Midwest tornado outbreak. It occurred on December the 10th and the 11th in the year of 2021. Normally, being that late of the year, you may be able to see tornadoes in this region. You wouldn't see tornadoes this north. And also in this individual tornado outbreak, there were 71 individual tornadoes. Other facts about tornadoes. The tornado-induced property loss is very comparable to hurricane-induced property loss, although the impacted area by an individual tornado is much smaller than the impacted area by a hurricane. This is another way to show the violent nature of a tornado. And then also tornado-induced fatalities are much higher than hurricane-induced fatalities. So indeed, we may not be able to prevent tornadoes from attacking us, but we may be able to find some way to reduce the impact of tornadoes. So one way we can do is to propose and implement tornado hazard mitigation strategies, including engineer hardening solutions, building your house stronger, or nature-based solutions. And to facilitate this, we need to simulate high-fidelity models to simulate tornadoes, to simulate the tornado structure interaction, to simulate the tornado community interaction. To simulate a tornado, at the very beginning, we apply this cylindrical computational domain. This is velocity inlet, this is pressure outlet. Air particles move up while rotating. This is a tornado. And how can we tell we did a good job? So at a certain height, we extract a tangential velocity distribution along the radial distance from the center to the edge, shown as the red graph. And the blue dashed graph is extracted from radar measured velocity data. So in terms of the core radius, and maximum tangential velocity, our results is very close to the radar measure data. And then by changing the boundary conditions, we can simulate tornadoes with different flow structures. Here, we have 4 subvortices. So when I did these simulations, the velocity light and the velocity input were from this is South Dakota, Spencer, South Dakota tornado in 1998. We got the data from the radar measure data, but it is only from one time incident because that is what I extracted from the published paper. And then, so since the velocity input is exactly the same at all the time instants, there's no time variation. And also, around the velocity light at anywhere, the velocity input is exactly the same. So no space variation. This cannot reflect the variability of real-world tornadoes in time and space. So to bridge this research gap, I collaborated with Dr. Guirong to couple CM1, Cloud Model 1, and CFD. CM1 was developed by Dr. George WHAM to model micro to mesoscale atmospheric phenomena. So Dr. Off used CM1 to model the 2011 El Reno tornado. So in civil engineering, besides Dr. George WHAM, and Dr. Neoff is also very famous because his spatial resolution is higher than others, and the highest that he went with is 10 meters. However, even this spatial resolution is not good enough for civil engineering structures to get the pressure on structural surface correctly. And this motivated us to collaborate with each other by copying CM1 and CFD. So the blue cylinder is my CFD domain. So the output of CM1 from the gray box will be the input of my CFD simulation. So this way, CM1 supplies the initial condition and time-dependent boundary condition to the CFD simulation. Driving CFD simulation using the flow that can reflect the variability of real-world tornado in time and space. And then the CFD model is based on large ID simulation. And then we applied this coupled simulation approach to simulate 2011 El Reno tornado again. So of course we cannot directly use CM1 data because the spatial resolution of CM1 is much smaller than the CFD, the spatial resolution of CFD. And what we did is we did the data interpolation of CM1 data at the boundary condition of the blue cylinder of the CFD domain. So this is the vertical plane. This is a vertical plane, and this is the photo taken from the field. So both of them are tilted. So at the height of 10 meters, we extracted the tangential velocity. So here, this axis is time. So as time evolves, look at the blue graph, tangential velocity increases, and pressure deficit increases. And that is to say, as the tornado evolves, the tornado becomes stronger and stronger itself. So and from here you can tell the orange graph is Coriolis, so it fluctuates around the mean value. So now you may have a question: what is the benefit of coupling CM1 and CFD? Here, I'm going to show you the pressure contour on a vertical plane. So this is from CM1, and this is from the coupled simulation. Did you see the difference? So actually this difference is because in CFD simulation, on the ground, that is free slip. And in reality, the velocity is equal to 0 on the ground. So I hope this this can show the couple simulation can improve the simulation to reflect the real world situation. And also we further compared the tangential velocity at a certain height, at a height of 100 meters. Here, the maximum value is here 88.5 meters per second. Here is 93. So it looks like when we use couple simulation, we got a higher tangential velocity. And also along the along the radial distance at a height of 100 meters, we extracted the tangential velocity distribution along height. Look at the red graph. That is from the couple simulation. It is higher than the CM1. And also, this is the pressure deficit. So here, the magnitude is higher. Pressure deficit is higher from the couple simulation. Looks like the intensity is higher when we use couple simulation than a CM1. And along the height, so red color is a couple simulation. It gives us a higher value than the CM1. So this is the pressure deficit profile along height. So here, bigger value, bigger magnitude from the couple simulation. And also we compared the maximum value. So if maybe we look at maximum resultant value from CM1, 88.2, from the couple simulation is higher. And the pressure deficit. So obviously this gives a higher value. So I want to summarize, when we use couple simulation, the intensity is higher. Intensity is higher. Maybe in reality it is like this. Just CM1 simulation, the spatial resolution is not as high as the couple simulation, and CM1 didn't capture the higher value in tornadic wind field. The whole purpose for me to simulate tornado is to find out the impact of tornado on the built environment. So by including the civil structure of interest in the computational domain, I can figure out the action of tornado on the building. So that is a pressure on structural surface. And also, based on this, we can get the total forces along 3 directions and total moments. And based on that, I can figure out whether it is damaged or not by comparing the wind loading and the resistance of a civil structure. And in order to get the tornadic wind effects on the civil structure more accurately, we not only include the civil structure of interest in the computational domain, but also its surrounding buildings. And then now let me show you how we applied the couple simulation to model tornado community interaction. We want to do this. We want to model, we want to use the most severely damaged community by 2021 Midwest tornado outbreak. So that is Bowling Green. That is around here in this track. So this tornado, as I mentioned, impacted 10 states, killed 89 people. 89 looks like it's not a big number, but if it is a casualty, that is a lot of people. And it caused $3.9 billion of property loss. So what we wanted to do is we want to develop a tornado community model, and then we want to reproduce the damage to Bowling Green, Kentucky. And so this way, we will get a calibrated tornado community interaction model. And then we can use a calibrated model for tornado resilience planning. To apply the couple simulation, we need Dr. Alf to provide the CM1 data of this tornado, 2021 Midwest tornado outbreak. Unfortunately, Dr. Alf didn't get a chance to do this CM1 modeling of this 2021 Midwest tornado outbreak. This inspired us to take advantage of the existing data. So we still use a 2011 El Reno tornado CM1 data, and then we will scale that, until we see the simulated damage is similar to the observer damage from the 2021 Midwest tornado outbreak. So it is a trial and error process. We modeled 42 buildings in this community. So to make our model simpler, we applied the archetype. So we assigned 6 archetypes to the 42 buildings, and each archetype is represented by one color. And this is the observed damage, so that is our target. So of course, the first trial will be original CM1 data of a 2011 El Reno tornado. So using the couple simulation, we can figure out the action of a tornado on each building. So like when a tornado passes, when the different parts of a tornado passes this individual building, what is the pressure distribution on structural surface? This is wind loading. By comparing the wind loading with the resistance, I can tell you which part will be damaged or whether the entire house is collapsed or not. So now if I use transparent to represent completely destruction, I use a black color to represent no damage. And then from dark gray to light gray to white, dark gray to light gray to white, damage extent increases. So this row of building are associated with this row of building. So in our simulation, they are completely destroyed. And in reality, they survived. So that is to say, the tornado intensity in our couple simulation is too high. And then it is natural to think of using a lower wind speed. So the lower wind speed, we reduce the wind velocity by 10%, 20%, and 30%. Of course, the pressure at the tornado center also changed. The pressure distribution at the pressure outlet also changed. And then from here, you can see that this is the raw data, and then 10% reduction, 20% reduction, 30% reduction. They are the tangential velocity. It decreases. And also, original data, 10% reduction, 20%, and the 30% reduction, and also pressure deficit decreases. By doing this scaling, the tornado intensity did decrease. And then, so by applying the same approach I just mentioned to you, we can determine the damage condition in each case. So original CM1 data, so in this case, the velocity reduced by 10%, 20%, and 30%. So again, based on the surviving building on this row, destroyed. We do have survival buildings here, survival buildings here, and these two will be ruled out. So only look at these two. Because here, these houses are completely destroyed. But in this case, we still have several buildings survived. And therefore, this one, the tornado intensity is too low. And therefore, by doing this trial and error, we can tell that by reducing the velocity of 2011 El Reno tornado by 20%, we can kind of reproduce the damage to Bowling Green, Kentucky. And then now with the calibrated tornado community interaction model in hand, let me show you how we can do tornado resilience planning. So as I mentioned, the two approaches. One is engineer hardening solution. So just build your house stronger. So let me use the residential wall structure as an example. Where can you make it stronger? So where do we often see the damage after tornado? That is roof. So we can do two things. Increase the roof sheathing installation strength. So here 6 means the distance between the two nails is 6 inches, and 12 means 12 inches. Obviously, this one has a higher roof sheathing installation strength. This has lower. And the connection, roof to wall connection, we use hurricane clips. So here means 2 hurricane clips are applied. Here means 1 are applied. So obviously this has higher strength. And we simulated 4 cases. In all the 4 cases, they have different resistance, roof sheathing insulation strength and roof to wall connection strength, but they have the same roof covering, asphalt. By using the same approach, now I want to show you which one is better in terms of resisting when the tornado. So here, so by comparing these 4 figures, in which figures do you see more transparent houses? That means more destroyed houses. Yes?
It's interesting that it seems like in the strongest case, though, some of that outer row had a, sorry. It looks like.
It should be on.
In the strongest case, case 2, yeah. It looks like some of the outer row actually had a little more damage than in some, like the top row of houses looks like there's some gray, whereas some of the other ones look black. You know what I mean? Like
I saw this.
So it's a more complex.
Yeah.
Okay. Yeah. I was just wondering if you could talk a little bit.
Thank you. Very good observation. So if we are checking in which figures you see more transparent houses, so that is in these 2 cases, we see more transparent houses, especially around this row. And then this is because only 1 hurricane clip were installed. So that is 1 hurricane. So that means that's a weak roof to wall connection strength. So in this situation, it doesn't matter whether you have a stronger roof sheathing installation strength or not. So which can be evidenced by the same or similar damage extent between these 2 cases. On the contrary, if we have more hurricane clips between roof and the wall, two here, so you can see that we have more houses survived. And then in this situation, if we have a higher roof sheathing insulation strength, more houses will survive. So for example, in this house, compared to this one, damage is less here. And also compared with this damage is less. And also compare this one with the white, this damage extent is more severe. This damage, this is more severe because lighter color represent more severe damage. And so that is a great observation. And then obviously this case with a stronger roof sheathing insulation strength and with a stronger roof to wall connection strength is a champion for tornado resistance. And we got the similar conclusion for other tornado intensities. Remember, this is the calibrated model, and if it is even higher intensity, even higher intensity, so the same situation. And then what I just talked about is engineer hardening solution. And then what will be the nature-based solution for tornado resistance? So actually, nature-based solution has been widely accepted for flood hazard mitigation. For example, for often flooded area, the government will buy out the houses and converts that land into wetland or parks. And what would be the resilience, nature-based solution for tornado resilience? Do you want to build your house at a location surrounded by mountains? Do you want to build your house underground? Do you want to build your house at the top of the hill surrounded by forest? Do you want to build your house on the slope of the house, or do you
simply want to build their house on a flat area. So it depends on how the terrain affects the tornado intensity. To study this, we simulated 5 cases. In the first case, we call that control run, no terrain, it's on the flat area. And then we simulate 2 hail cases, 2 escarpment cases. 0.25 means the weak slope, and 0.5 means the steep slope. So how do I measure tornado intensity? I use 2 parameters. One is the pressure deficit, or we can call that the maximum negative pressure at tornado center. And the other one is wind speed. So now let's see how the terrain affects the pressure deficit. So the red color is a control run, and all other colors are for the cases with one type of terrain. So this is the graph with the red color. And then look at the vertical axis. The vertical axis, that's the pressure deficit, 20, 40, 60, 80, 100. So gradually increases. So here, now we see for the cases with any type of terrain, they are below the red color. They are below the control run. So that is to say, the presence of terrain increases the pressure deficit, increasing tornado intensity. Now let's look at the velocity. So first we want to look at horizontal resultant velocity, and then we'll look at vertical velocity. So this is the horizontal plane at the height of 10 meters. So here, the color bar represents the magnitude of the velocity, resultant velocity. So blue represents 50 meters per second, and red represents a higher, for example, around 150 meters per second. So this is for control run. And for all other cases, we have a dark red color, the red color in a long length, and a very dark color, and very dark red, and dark red. So, so I can tell you that the presence of terrain increases the horizontal resultant velocity, increasing tornado intensity. And similarly, for the vertical velocity, we can tell that so now I realize this bar is not correct. So for the vertical velocity, the maximum value is about 50 meters per second. But they are all correct. But from here, we can tell that we have a dark red color, red color, red color, red color. So again, the presence of terrain increases the vertical velocity. So now my conclusion is any type of terrain increases the tornado intensity. If I ruined your plan to build your dream house in a location with such a great view, I apologize. I'm just want to providing you with the information and the knowledge. And so hopefully you can develop your own wisdom to make an informed decision on the location of your future house. I also collaborated with the 2 social scientists from University of Oklahoma to improve the safety of mobile homes by increasing the integrity of mobile homes. So what we did is to figure out the action tornado on mobile homes, and we did we tried to figure out the function of the in-ground anchoring system. With the in-ground anchoring system, although in a low intensity tornado, we still have some deformation, but it will not flip. And for this is called PAN type, no in-ground anchoring system. So even at a low intensity tornado, it can flip, it can kill people. Also, currently we are using the produced data based on the physics-based modeling, developing the virtual reality animation of tornado disasters. So the goal here is to improve the risk awareness of the general public. So although we know that a roof is the first line of damage under tornadoes, to reduce the tornado impact, if you install a stronger roof, you think that can reduce the impact to your house, but it may not be true. So this only be effective if the entire community are doing the same thing. The entire community are reinforcing their roof, doing a stronger roof, because otherwise, even though your house is good enough, and those weak houses can be damaged, severely damaged or destroyed, and they will form windborne debris. They can still severely damage your home. And then, besides the numerical simulation, when I do presentation for my numerical simulation results, they always ask me how did you validate your results. So besides saying that my results are try to be consistent with the radar measure data, we developed the tornado simulator, physical tornado simulator in the lab from here to here. That's 22 feet. And swirling wind flow is generated underneath. And last year, from last October, National Science Foundation funded $14 million to design a larger tornado simulator. I'm one of the co-PIs. And so they want this diameter to be 10 times of this one, 10 times of mine. So let me tour you the facility.
Technology, home of the Center for Hazard Mitigation and Community Resilience and the Wind Hazard Mitigation Laboratory. Tornadoes are so violent that sensors don't survive to record wind speed and pressure on civil structures. To record tornadoes' intensity, post-damage surveys use EF scales based on the extent of damage. Current technologies offer no way to measure the real wind speed, the interaction between tornadoes and structures, or structures' failure mechanisms under tornadoes. To find tornadic wind effects on civil structures in order to better rebuild, Dr. Yan and her group bring tornadoes into the lab. With the support of S&T's College of Engineering and Computing, the Office of Vice Chancellor for Research, and the Sinkfield family in Missouri, S&T built the tornado simulator in April 2022. The powerful fan generates 139,000 cubic feet per minute flow rate with a static pressure of 1.6 inches of water, which can produce wind that can be scaled up to a high-intensity tornado. The fan's 84-inch diameter can potentially produce a swirling wind flow with a core size of 2 meters in the lab. The bridge crane enables the simulator to maneuver along a straight path to simulate the translation of a tornado. The translating speed can reach up to 2.5 meters per second. Dr. Yan's group has developed the facility's CFD model as the digital twin of the physical simulator, which allows stakeholders to visualize detailed wind flow across the entire wind field and better understand the interaction between tornadoes and structures and the failure mechanisms of civil structures under tornadoes. Essential information to develop innovative tornado hazard mitigation and adaptation. Because the facility has both physical and digital components, it is known as the Tornado Simulator Twins. The research facilitated by the Tornado Simulator Twins will help researchers develop new knowledge and technologies to achieve 2 BBBs: build back better after a disaster and build better before a disaster. We invite engineering researchers, social science researchers, practitioners, and other stakeholders to conduct testing in the Sinkfield, Missouri Tornado Simulator Twins facility. Missouri S&T is ready to contribute to tornado resilience.
Besides numerical simulation and experimental testing, we will also go outside to do reconnaissance surveys after tornado events. So for example, 2021 May was a tornado outbreak. This is Mainfield, Kentucky, and also 2019 Jefferson City tornado. That is only 60 miles away from my university. And so actually, it occurred on May 22nd. And so you all know 2011 Joplin tornado. So it also occurred on the same day, May 22nd, 2011. So now I want you to remember. So May is a tornado month, a tornado season. So people say March, April, and May are tornado seasons. So we flew drones to get overall damage condition. We also go door by door and to figure out the damage condition to each building. We also apply high accuracy LiDAR to get a detailed damage information. In summary, we improved the tornado simulation by coupling CM1 and CFD, taking tornado simulation or tornado community interaction simulation to the next level. I want to take this opportunity to thank the father of the CM1 developer, Dr. George Bren. And then, so this coupled CFD simulation can be used by meteorological researcher to study tornado dynamics, can help civil engineers to study tornado impact. And the related research findings can be used to inform decision makers or policy makers to allocate their limited resources to the most vulnerable population to take proactive actions. So I want to thank the financial support from National Science Foundation, from NOAA, and U.S. Army Corps of Engineers. Also, I want to thank my team members for their hard and efficient work. So these are my current team members. Before I wrap up my talk, I want to invite you to come to St. Louis, Missouri to attend the next America's Conference on Wind Engineering. I'm going to chair this conference. It is an international conference, so it includes attendees from both North America and South America. It will be on May 19 to 22nd. And I look forward to greeting you at your arrival in St. Louis, Missouri next May. Thank you.
Thank you. We have plenty of time for questions.
Yes, sir.
Yeah, thank you very much for a really interesting presentation and some great results. I'm kind of curious about the tornado chamber, the experimental chamber you described. Are those packing peanuts that you had kind of floating around?
Yeah, correct. That's a packing stuff.
Yeah, packing
foam,
okay.
Yeah.
And so is that how you use? Is that what you use to measure velocity?
I use the Copro probe. So here I just one type of visualization. I don't have a PIV, but I did use the Copro probe to measure velocity everywhere, and I do have all the results. That's a master student did all the measurement in the summer.
Yeah, cool, interesting.
Yeah,
Thanks.
well, I would like to share it with you after so I further review the results. Thank you. Good question.
It's a clever way to visualize.
I'm thinking in other fields, for example, aircraft design, they don't use wind tunnels anymore. And this is kind of a wind tunnel you have in some sense. Do you think we're at that point now where computations?
Yeah, are you saying that in
almost take
aerospace
that over?
engineering, the CFD simulation is accepted already? Yeah, actually in civil engineering, let's not talk about the tornado. Let's just talk about the straight line winds, the synaptic winds. Currently, they are still trying to use a wind tunnel if it is a special type of shape, special structure with a special shape, the practitioners still believe the results from wind tunnel testing. And we are working hard to form committee to see whether in the future the CFD simulation can replace wind tunnel testing, at least for straight line winds. Currently in Japan, the CFD simulation is legal to be used to determine wind loading for civil structures. But in our country, it's not. That's a very good question. Thank you.
Thanks for the great presentation. I had a little maybe technical question. The CM1 original simulation you said had free slip, lower boundary condition, but then in your CFD simulation you said it was no slip. Is that right?
Correct. No slip.
So it's going from free slip to no slip inside
Correct.
the CFD domain.
Correct.
But then in your other simulations you did later for where you were actually simulating the impact on the terrain, those were free slip as well? Is there?
No slip. It's still no slip.
You said no friction. That's why I was confused.
So the CM1 simulation, CM1 on the bottom, on the ground, is no slip wall. But in ours, it is a slip wall. Even when it translates, there's a slip wall. Yeah.
Okay, so like in the slide that you showed with the different terrain, you said no friction. That none of them had friction.
That is a flat. So what I'm talking about is if there's a hail or this is flat. So in one case, the control run is flat, and in other cases there is a hail or there's escarpment.
Okay.
So that means the elevation. That means the ground plane, there's elevation. There's a variation of elevation if there's a terrain.
Right, right. But you model friction with the ground in that. You said you're not modeling, so is that a free slip simulation?
It is not free slip. It is still a slip wall.
Okay.
Yeah, the moving is achieved by doing the relative motion because CM1. That is a frame relative calculation. You always calculate things in that computational domain. And then after you got the results, you add U move and V move. So when I do the coupling of CM1 and CFD, so I just move the frame in the opposite direction. I achieve the moving of the tornado.
Okay, thanks.
That's a very good question. Thank you.
Thank you for your interesting presentation. So I'm coming out of the weather community, and for me, high-resolution modeling is 1 kilometer, 3 kilometer grid spacing. So you're showing animations where you have actual houses in the CFD model. I may have missed it. What grid spacing are you using in the CFD model? What time step? And does debris actually fly around in the simulation, or is it just rendered?
In this simulation, I didn't include windborne debris. And regarding the mesh size, in the horizontal plane, it is less than 10 meters. And in order to get the boundary layer correct, so for example, if this is a house, so on the surface of the building, the thickness of the first layer is 0.01. And then I use an inflation technique, and by using the ratio of 1.2, and I have 100 layers to get the boundary layer correct. Okay. So this is why we call that high fidelity. I mean, the very fine resolution in order to get the wind pressure on structural surface correctly. Okay. Thank you.
Yeah, thanks for the talk. I had a question about your simulation of the damage patterns in the neighborhood. So you matched the simulated damage with the observed damage, and to do so you dialed up and down the wind speed. But I wondered about the other drivers of damage, because you've got the resistance of the structures that must have some uncertainty in how the buildings respond to the the wind pressures. So
Yeah, I think this is a very good question. I did skip this part. In order to figure out the damage extent, we need to have the definition of a damage state. What we used is for example, the damage state. Actually, that is a combination of the damage to different components. So for example, the roof or cover failure, roof deck failure, how many windows or doors failed, or the roof structure failure, or roof cover failure, or roof structure failure. And so you need to have a certain combination. For example, if it is it 20% of a roof cover failure if it is greater than 20%, and also no roof deck failure and one window or door are damaged, that is defined as a DS. We need to have the definition. We need to have the definition of the damage state, and then from no damage to minor to moderate to severe to completely destruction. And also for resistance, we do need, as you mentioned, it is based on statistics and probability. For example, for roof sheathing insulation strength, we have mean value. We have the deviation, standard deviation, and then based on this, we will generate a great number of cases, for example, 10,000 cases of resistance. And also for my loading I obtained, I also add some noise and then to generate 10,000 cases, and then I can do the comparison for each case. I will see how many of them for, what is the percentage for this, and what is the percentage for this.
okay, yeah, I hadn't realized it was probabilistic. Yeah, that makes sense.
Yeah, thank you.
Since we're on the topic of this one thing I noticed in the diagrams from the simulations of the houses is that a lot of them were either totally damaged, and then there were a handful that were undamaged, but not many in between. Is that more a reflection of the fact that whether the house is destroyed or not is just really sensitive to the pressure on it, or is it more just the really extreme kind of spatial gradients in the tornado winds, or maybe both? I don't know.
So actually, the tornado, it has, for straight line winds, so the major factor to cause damage is wind speed. And for a tornado, you not only have a high wind speed at certain radius, core radius, but also have a low pressure. And also here, I want to show you, even for the same building, if it is lucky enough, it will be through the center of the tornado path, and then the core radius will pass the building the first time, and then the center will pass the building, and then if it is still not damaged, this will experience the high wind speed the second time. So what I'm saying is here, if your house is strong enough, when the high wind speed passes you, it is not damaged, and then it is still enclosed. And then when your core radius passes this, that means your outside, that is low pressure, lower than atmospheric pressure. And inside, it is a standard atmospheric pressure, and total pressure will be upward. So that is to say you will experience a very high pressure. Now, although the wind speed didn't damage your structure, the high uplift force from atmospheric pressure may damage your building. And if it is still not completely damaged, it will experience the high wind speed. Did I answer your question? Okay, thank you.
Yeah, I agree with everybody. This is a great talk, and I think you have so many questions because you're teaching us things. And I did want to ask again about that one plot, if you could show the roof strength, because I don't think I asked it very clearly the first time.
I think you were talking about this, right?
Yeah, so this, and then if you go a few more and you show the neighborhood with so two more to slide 43, I think.
Okay, here.
This one, yeah. So, because actually what I was interested in is, so case 2 has the strongest roofs because it has the 2 hurricane clips and it has the nails closest together. very fascinating. But it looks like in case 2, like if we look at, house number 5 or whatever, it's actually more damage than in case 4. So it's a dark gray and the other one is black. So it's a little bit more damage. So that was actually what I was asking about.
Okay.
And I think it's probably because.
You were talking about this is kind of black.
Yeah.
This
and
is
it's probably
gray.
because you're saying that there's lots of different ways it could be damaged. It's
Yeah,
not
actually,
just the roof. But I was really interested in
Yeah,
this.
you are correct. The data are correct. So there's a detail I didn't share it with you because if I shared too much details, it may confuse you and I may not have time. So actually there's another detail I didn't share with you, and thank you so much for bringing this out. So actually, did you see that tornado paths are not the same at all?
Okay.
Something like this here, you can see the distance. The distance determines the damage extent. And for different cases, for different simulation cases, we figure out the tornado path is not the same.
Well, and actually that makes sense.
Yeah,
because it's hard to fully control
Yeah.
the path when you're changing the wind speed. So
And the whole purpose is to try to make our simulated damage. We are manipulating things to try to make our simulated damage to be consistent with the observed damage. So this way we treat it as a calibrated model.
it's still very robust results. It's very good. I noticed that and I was like, oh, why is that?
So and I really appreciate that you ask this question, giving me the opportunity to bring more details to you. Thank you.
In many of these big tornadoes, the vertical motions in the center of the tornado are as strong as the tangential winds often. Does your CFD model reproduce that kind of a tornado? Where at the axis you have this very strong low-level jet right at the core of the tornado?
Yeah, I think in CFD simulation, we can do a lot of things. We can definitely easily by adjusting the parameters to produce a tornado at high intensity. Yeah, just normally what we do.
Yeah, it's not just the tangential winds. But
You mean the updraft? So normally there's a downdraft. So normally tornado, at the center you have downdraft, and on the two sides you have updraft.
That's not true. There are a lot of tornado structures depending on this world.
So if it is a one cell, if it is one cell, it is very rare. To me, it is very rare. We also try to simulate that. In certain cases, we are not able to. We will try parameters, and it's very difficult for us to find a case to only have updraft, no downdraft. And if there's a downdraft, we call that a two-celled single vortex tornado, but a single cell tornado, there are one cell and two cell or multi-cell. We sometimes we can achieve just their one cell, all updraft.
You need to consider that. I think it's more frequently observed than you're suggesting.
But even in the two-cell vortex, you have multiple vortices. Those sub-vortices have intense. They're like intense end-wall vortices.
Right.
Very strong updraft. So if you get hit by one of those, even if the whole structure
I
is two-cell.
I agree with you on that. It's a very it's more dangerous. Multi-vortex tornado is more dangerous than a single vortex tornado.
Any other questions? All right, well, let's thank Grace.
Yeah, thank you very much.